just as we did with kinematics, we'll have a problem-solving procedure to use with Newton's second law problems. Let me show you how it works. Generally, you want to do these three main steps. Draw a sketch of the situation, then draw what's called a free body diagram. This is like a technical diagram in physics that shows all the forces acting on an object. And then write down and solve the Newton's second law equations for whatever unknowns you're looking for. So let me go into more detail about this free body diagram. This is kind of like a blueprint in physics. You'll identify your object of interest. So we're only going to look at one object at a time. So pick the one object that's the most interesting, the thing that you're trying to solve for in the problem. That will be your object of interest, your OOI. Then choose a convenient coordinate system to use. That comes with some experience. A lot of the time it'll just be X horizontal and Y vertical, but there are some other more unusual situations where you use a different coordinate system. Place your object of interest at the origin. Identify the forces acting on the object of interest, not forces that the object of interest exerts on other things. And then draw and label the forces that are acting on that object. Now, it's traditional to use certain letters for different types of forces. We haven't learned about all these forces yet, but we will over the course of this week and next week. You don't have to use these letters, but these are kind of traditional. There's a capital N for normal force, a W for gravity, T for tension, lowercase f for friction, R for air resistance or water resistance, and just kind of a generic force, we'll use a capital F. Then you'll solve your equations. You write down your force vectors in component form, so you might have to do some trigonometry to get the x and y or maybe z components of each of those forces. Write down those Newton's second law equations in each direction, and then use some algebra to solve for whatever unknowns you're looking for. So this is kind of abstract as I'm talking about it. The way you learn how to do this is through examples. So over the next few videos, I will do several examples so you can see how this process works. And I want to start with a simple example of an object that only has one force acting on it. This is the freely falling object like we were studying in our kinematics lessons. So remember we described the motion of a projectile. So here's a sketch. Here's projectile motion. Now let's analyze the forces on it with Newton's second law. I'm going to draw this free body diagram, F, B, D. And let me just pick one particular instant in time. This is kind of a generic instant in time for this motion. I'll just concentrate right here. And we'll go through this process. Identify my object of interest. Well, the object of interest is this projectile. Maybe this is a ball. So that's the thing I'm going to focus on. I don't worry about the person who threw it. I don't worry about the ground. I don't worry about the air. I only look at the forces acting on that ball, on my object of interest. Next, I choose a coordinate system. And the coordinate system I'm going to use is just a regular horizontal, vertical, XY coordinate system, like so. So here's my coordinate system. X is horizontal, Y is vertical, up is positive, down is negative, to the right is positive, to the left is negative. I place my object of interest at the origin of this coordinate system. There it is. Now, I identify the forces acting on this. Well, when you throw a ball up in the air, after you let it go, there's only one force. That's the gravity force. And gravity always pulls straight down. After you let this thing go, there's no horizontal forces, there's no other vertical forces, there's only that gravity force. So I'm going to draw this force vector, well I just drew it, now I'm going to label it with a W. So we use W for gravity. Remember, W means weight, which is another word for the gravity force on an object. And it's traditional to put subscripts labeling what object is causing the force, what object is receiving the force. So I'm going to say this is the gravity force of the Earth pulling on this ball. W-E-B, Earth ball. And that's it. That's how you draw the free body diagram for this problem. Now I want to point out something about the situation that sometimes students get confused about. Even though the ball has a horizontal velocity, even though it's moving in the x direction, there's no force in the x direction. Once you let go, after you've thrown the ball, it continues to move horizontally because of its inertia, because of Newton's first law. Horizontally, that x component of velocity is the same the whole time because there is no horizontal force. Therefore, the velocity doesn't change. In the vertical direction, in the y direction, the velocity does change, right? It goes up and then goes down. That's because there is a force. There is a net force in the y direction. So all this stuff that we just took for granted when we were talking about kinematics now makes sense in terms of what we've learned about Newton's laws. All right, we've got our free body diagram. Now what we need to do is write down Newton's second law and solve those equations. So we have an x direction and a y direction, and I'll do both of them even though you don't really need to do the x direction, but I will anyway. So Newton's second law in the x direction says the sum of all the forces in x equals mass times ax. And if you look at our free body diagram, there are no forces in the x direction. And if you divide both sides by m, then you find that ax equals 0. So we've now shown that there is no acceleration in x, which is what we've been saying all along about these projectile motion problems. On the other hand, Newton's second law in the y direction sum of the forces in y equals m-a-y. Well, we've got this gravity force and is directed downward, so I can indicate that direction with a minus sign and write the magnitude of the force. And we learned in the previous video that the gravity force when you're on the surface of the Earth has a magnitude of m times g. And those two m's cancel out, and so we find that the acceleration of this ball is minus g, or minus 9.8 meters per second squared, which is what we have been saying all along, but now we've shown where that comes from using our new Newton's second law problem solving method.